So in this video, I'm going to talk about the solutions for the questions which appeared in Thermal and Stat in IIT-JAM 2016. The first question is, a spherical closed container with smooth inner wall contains a monoatomic ideal gas. If the collisions between the wall and the atoms are elastic, then the Maxwell speed distribution function, that is dnv by dv, for the atoms is best represented by. So first of all, it should be clear from the statement that it's a three-dimensional speed distribution. So therefore, the expression for the three-dimensional system will be valid here. So the required expression, so that is in 3D. In 3D, the Maxwell speed distribution is given by dqn, which is equal to 4 pi n multiplied by m upon 2 pi kt and its power 3 by 2 and then v square exponential minus m v square by 2 kt and then multiply by dv. So this is the Maxwell speed distribution in 3 dimension, and further it can be rewritten as, so we will bring dv on the left hand side, so then it will give, and let's denote that as f of v, okay, and that is equal to dqn by dv, and we are left with then only the 4 pi n and m by 2 kt as it is, m by 2 pi kt power 3 by 2 and v square and exponential factor, exponential minus m v square upon 2 kbt. Okay, now let's call this as equation 2. Now we can determine its behavior as a function of speed b, okay, under two extreme conditions, and then we can determine in between by simply applying the by equating its differential of fb with respect to b equal to 0. Okay, so let's try to understand its functional behavior under two extreme conditions. That is, the first is that when v approaches 0, okay, so that is when speed is 0, okay, then what happens to this function fv, okay. So if you just take a look at these two quantities, these are the constant quantities, okay. For fixed type of gas molecule, m is constant, and if temperature is fixed, so then this quantity is going to be a fixed number, okay. Now, so when b approaches 0, so then in this approximation, this quantity, this also approaches 0. So under this approximation, fv, that also goes to 0. Now in the second case, when speed, it's very large, let's say it approaches a very large value, or say infinity, okay. So in that case, fv can be approximated as v square. So because all these quantities, they are constant, then the behavior of fb will be determined by the product of v square and exponential minus mv square by 2 kt. So for a very large value of v, the exponential factor will dominate, and in this situation exponential minus mv square by 2 kbt, it will approaches 0. So therefore fv will approach to 0 in this case also. Now the situation is in between the behavior of the fv as a function of v can be determined by simply equating dfv by dv, that is equal to 0. So this will gives us the point of gaining the maxima, okay. So by simply equating this to be equal to 0, we can obtain a value of v at which this function gains a maximum value. So therefore the part C here, this correctly represents the behavior of the function fv given by the equation 2 here, okay. Because here when v approaches 0, this which is fv, this also approaches 0, and when b approaches infinity, the function also approaches 0, and somewhere in between it's acquiring a maximum value. So therefore C is the correct option here. C is correct here. For an ideal gas, which one of the TS diagram is valid? Okay, so we can identify the correct diagram with the discussion as follows. So here basically we have to compare the isochoric and isobaric process. So we are given a isochoric and another one is the isobaric process. Okay, so in isochoric process, volume is constant, which means dV, that's 0, and in a isobaric process, pressure is constant, which means dP, that is equal to 0 here. Okay, now in a TS diagram, so in general what we can do is, in general we can write dQ, the heat change involved, that is equal to T times ds. Let's call this as equation 1. Okay, now when the process is isochoric in nature, so for an isochoric process, and with 1 mole of an ideal gas, so I can write dQ, that is equal to n Cv dt, because n we have taken as 1, so it is simply Cv dt. So now this is for the isochoric process. Okay, the volume will be constant, so in that case dQ can be replaced with Cv dt. Okay, so when we compare 1 and 2, so because dQ, that's TdS, and here from equation 2 it is Cv dt. So from these two equations, 1 and 2 implies dt by ds, sorry, it is ds basically, dt by ds at constant volume, that is equal to T divided by Cv. So this is equation 3. Now similarly for an isobaric process, so for an isobaric process, we can write dQ, that is equal to Cp dt. Let's say that this is our equation number 4. Now compare equation 1 and equation 4 here. So by comparison, again we can write dt by ds, but now for the isobaric process at constant P, that is equal to T divided by Cp. So let's call this as equation 5. Now remember that for an ideal gas we also have the relationship between Cp and Cv, because Cp it's larger than Cv. Okay, so this means that if you just compare equation 3 and equation 5, okay, because both the equation they are giving the value of dt by ds, that is the slope of the TS diagram, okay, under two different conditions, one at constant volume and another one at constant pressure. Now because Cp it's larger than sorry, it should be Cp here, not Cv. Okay, because Cp is larger than Cv, so therefore, so this condition implies that dt by ds under isochoric condition, that's at constant volume, it's going to be larger than dt by ds at constant pressure. Not only it's going to be larger, but these are the positive quantities in fact. Okay, so they have positive slope basically. So the positive slope, see, we can neglect option D and option D, because here the isobar it's having a here up to this point it's having a positive slope, and then it's changing its slope. So therefore it's not the correct one. This is also not the correct one, because here these two curves beyond a certain point they acquire that they are changing the behavior of the slope. Okay, so here let's it's also correct, it's also wrong. B is also wrong here, because the isochore is having the smaller gradient here. Okay, but here in the option A, the isocore is having a slope which is larger than isobar. Okay, so that's what we are talking about here. So here dt by ds, so that means it's simply the slope of the curve which is given to us. So in option A, the slope of the isocore, it's larger than the slope of the isobar. So therefore option A is correct here. Therefore A is the correct one. Okay. If U, F, H and G represent the internal energy, Helmholtz sphere energy, enthalpy and Gibbs sphere energy respectively, then which one of the following is a correct thermodynamic relations? Okay, so whenever you encounter such type of question, the only thing that you have to keep in mind is that you have to simply remember only 4 expressions, and just by remembering those 4 expressions, you can not only remember all these the thermodynamic potential relations, but also the Maxwell relations. You can easily reproduce the Maxwell relations also. And what are those 4 thermodynamic potentials? So I will explain them one by one here quickly. So the first thermodynamic potential is that is the internal energy. That is simply the statement of the first law of thermodynamics. Okay, so du, that is equal to TdS minus PdV. Okay, so that's our first thermodynamic potential. Okay, now the second one, so after writing all these, then we will check which one is correct here. Okay, next one is the enthalpy. So enthalpy is defined as H, that is equal to U plus PV, and from here one can easily calculate the small change in the enthalpy, which is given by dH, that is equal to du plus PdV plus V dP. Okay, now substitute the value of du from equation 1 here, so that will gives us TdS minus PdV plus VdP. So PdV will cancel with PdV, so we will be simply left with dH, that is a TdS plus VdP. Okay, so this is dH here. Okay, so let's call this as equation 2. And similarly, the third thermodynamic potential, that is the Helmholtz free energy, F, that is equal to U minus Ts, and from here I can write immediately dF, that is equal to du minus TdS minus S dt. Okay, and now again substitute the value of du. Okay, so that is equal to TdS minus PdV minus TdS minus S dt. So TdS and TdS, they will cancel with each other, and we are left with a very simple result, minus PdV minus S dt. So let's call this as equation 3. Okay, so that is dF basically. Okay, similarly for the fourth case, the definition of the Gibbs free energy, G, that is H minus Ts. Okay, so this implies dG, that is equal to dH minus TdS minus S dt. Now substitute the value of dH from here, from equation 2, that is equal to TdS plus VdP minus TdS minus S dt. Okay, so TdS and TdS will cancel with each other, so that dG is equal to VdP minus S dt. So this is our equation 4. Now let's compare with the given option. So in the first option, it is du, that is equal to PdV minus TdS. So du, it's wrong. Okay, what was the second one? dH, that is equal to VdP plus TdS. dH, that is BdP plus TdS. Yes, this is the correct one. And what about C? dF, that is equal to minus PdV plus SDT. No, it's wrong. We are having a wrong sign here in the C. So this is also wrong. And dG, that is equal to VdP plus SDT. No, VdP minus SDT. So this is also wrong. So therefore B is correct here. One mole of an ideal gas with average molecular speed V0 is kept in a container of fixed volume. Okay, if the temperature of the gas is increased, so we are given the condition such that the average speed of gets doubled. Okay, so let's try to understand this problem. So first of all, because in the option the mean free path, the statement related to the mean free paths are given. So let's write the expression for the mean free path and then try to understand that which option is the correct one here. So the mean free path under first order approximation is given by under first order approximation is given by lambda, that is equal to 1 divided by under root 2 n sigma, where sigma is the cross-section area of the gas molecules. Okay, 1 divided by under root 2, and n is the number density. Okay, so n, that is equal to basically n by v. Okay, so under root 2 n and then pi d square. Note that d is the diameter of the gas molecule here. Okay, d, that is equal to the diameter of gas molecule. Okay, and n, as I said, it's the number density, and this can be rewritten as n by making use of the ideal gas equation, PV, that is equal to n kBT. Okay, so from here, so we can write this implies n by v. Okay, that's a number density, so n by v will be p, that will be p upon kBT. And if we make this substitution, this is what, this is equal to the number density, and we can make a substitution here. Okay, so in this case the expression for the lambda reduces to lambda, that is equal to 1 because n, that is p divided by kt, so kt will come in the numerator, kt divided by under root 2 and then p and pi d square. Okay, so now we will try to understand this expression for the given condition. So we are given the condition that the 1 mole of an ideal gas with average molecular speed v0, it's kept in a container of fixed volume. Okay, so this is also one of the condition. So when the volume is fixed, okay, so let's try to understand the point from here. PV, that is equal to n kBT. So when volume is fixed, okay, volume is fixed, then n, it's also fixed, k is also fixed. So under the condition of fixed volume, what happens, what is the relationship between P and T? So that means for fixed volume, pressure is directly proportional to T. Okay, so now if pressure is directly proportional to T at constant volume, so that means when the temperature is increased, the pressure will increase in the same proportion. Okay, so that means in that situation, which is the given condition here, the mean free path lambda will not change. Okay, so let's take a look at the options which are given. The mean free path of the gas molecule will increase. No, this will not happen. The mean free path of the gas molecule will not change. Yes, V is the correct option here. So that means the remaining options, they are also going to be wrong. The mean free path of the gas molecule will decrease. No, this is also wrong. The collision frequency of the gas molecule of the wall container remain unchanged. No. So here B is the correct option here. PV diagram below shows 3 possible paths for an ideal gas to reach the final state F. Okay, so we are given a PV diagram where 3 different processes are shown to us. Okay, so let's take a look at the diagrams here. That's a P versus V diagram. Okay, so now we have to identify the correct option out of the given 4 options. Okay, so let me draw the diagram again, and then we can figure it, so that we can figure it out. This is process 3, and this is process 2, and then we are having process 1. Okay, this is process 1. Okay, and this is the initial equilibrium state, and this is the final equilibrium state. Okay, now, so in order to obtain the correct option, so I'm going to make use of the first law of thermodynamics here, du, that is equal to dq minus dw. So let's call this as equation 1. Okay, now, so when we just take a look at these 3 different processes, the initial equilibrium state and final equilibrium states, they are the common for the all these 3 different processes. So that means, which indicates that because internal energy, it's a simply what you can call, it's a perfect differential basically. Okay, it doesn't matter which path we are following, the as long as the initial equilibrium state and final equilibrium states, they are identical for three different processes, the corresponding internal energy change, it's going to be identical in all these three cases. So that means du1, this is going to be equal to du2, and this is further equal to du3. So that means in all three processes the internal energy change is same. Internal energy change is same. Okay, and this is only true when initial and final equilibrium state for all these three different processes, they are identical. In case they are different, then you cannot make use of this result. Okay, now another point that we can note from the given diagram. So because the in a PV diagram, the work done under the curve. Okay, so for instance, if you are having this process 3 here, okay, the by following path 3, the corresponding work done will be given by the area under the curve. Okay, so this means in process 3, the corresponding work done is this much, the shaded area here. Okay, it's a PV diagram. Okay, so that means and if we just compare the work done in three different processes, so for the process 2, the corresponding work done will be given by, okay, this is a P versus B, and for the process 2 between same equilibrium state, the corresponding work done will be this area. Okay, this is for process 2. Similarly, for process 3, the corresponding work done will be between the same equilibrium states. So this, the shaded area, this will give us the corresponding work done here. Okay, so now as we can see from these diagrams, this is process 1. So from here we note that dW3 it is larger than dW2, and it is further larger than dW1. So that means work done during process, it's largest. Okay, so that's the second point basically. So this is our first point that we the conclusion that we drew from the discussion, and this is our second conclusion. And based upon conclusion 1 and conclusion 2, we can draw the conclusion about the dq also. So let's call this as equation 2, and this as equation 3. Sorry. Okay, so equation 1, equation 2 and equation 3 collectively they implies that to keep the internal energy change same for all three different processes, this ensures that dq3 is larger than dq2, and it is further larger than dq1. And the reason for this statement is that because here du1, that is going to be equal to du2. Okay, so to ensure that the difference it is exactly identical, so dq has to be larger in dq2 has to be larger as compared to dq1. Okay, so this is our fourth result here. So therefore, let's take a look at the options which are given to us. In the first is the work done by the gas is maximum along path 3. Yes, that is true. So that's what we just noticed here. Okay, now what about option B? Minimum change in internal energy occur along path 2. This is wrong. The change in internal energy is same along all these three paths. Okay, maximum heat transfer is for path 1. No, maximum heat transfer is for path 3. So this is also wrong. The heat transfer is path independent. This is also wrong. Heat itself basically a path dependent quantity. So only in one particular case, which is the adiabatic process, the it's not that. Sorry, I made a wrong statement. Okay, so it's the heat transfer, it's a path dependent quantity basically. So therefore A is the only correct option. A cylinder contains 16 grams of oxygen. The work done when gas is compressed to 75% of its original volume. So that means if we assume that V1 and V2 are the initial and final volume, so we are given that V2 by V1, it is 75%. So that means 75%, so that is equal to 0.75 basically. Okay, at constant temperature. So temperature is given to us, temperature, this is 27 degrees Celsius, which is 300 Kelvin. Okay, and the value of the gas constant, it's also given to us, R, that is equal to 8.314 joule per mole per Kelvin. Okay, and okay, So what else information given to us? We are given a 16 gram of oxygen. Okay, 16 gram of oxygen are contained in the cylinder. So from this information we can evaluate another quantity, which is the number of moles. So number of moles is equal to the given mass, which is 16 gram, and divided by molecular mass of the oxygen, which is 32 gram. So from here we note that the number of moles are 0.5. okay, now so the work done, we have to evaluate basically the work done in this process. Okay, so the work done is given by, so it's a constant temperature process, it's given, it's an isothermal process. So work done in an isothermal process, this is equal to nRT ln final volume divided by initial volume. Okay, so n we have evaluated, so n is equal to 0.5 and then multiply by r, which is 8.314. okay, and then multiply by the temperature, which is 300 Kelvin, and then ln natural log of B2 by B1. So B2 by B1, it's also given to be 75%, so ln 0.75. okay, and after evaluating these results, so this turns out to be equal to minus 358.6 joule. So this is our answer. So let's continue with the next question. The statement is, an aluminium plate of mass 0.1 kg at 95 degrees Celsius is immersed in 0.5 liter of water at 20 degrees Celsius, kept inside an insulating container, and is then removed. Okay, if the temperature of the water is found to be 23 degrees Celsius, then the temperature of the alumina plate is degrees Celsius. Okay, so we have to find the temperature of the aluminium plate, and some information is given to us. The specific heat of water and aluminium, they are given to us, and the density of water, that's also given to us. Okay, so here let's first write what is the information that is given to us, and then we will make use of the principle of calorimetry, and then we will try to solve this problem in a very simple way. So the mass of aluminium that is given, this is equal to 0.1 kg, and the heat capacity, it's basically specific heat, not the heat capacity. So that is C aluminium, this is given to be 900 joule per kg per Kelvin, and further the initial temperature of the aluminium, that is given as T aluminium, and I'm writing as fix I for initial, that is equal to 95 degrees Celsius, and this is further equal to 273 plus 95, and that will be 368 Kelvin. Okay, now what are the parameters for the water? The mass of the water, that is equal to, basically the volume is given, so that can be converted into mass, because the density of water, that is rho water, that is, it's given 1000 kilogram per meter cube. Okay, kilogram per meter cube, and the volume of water is given as VW, that is 0.5 liter. Okay, and this is equal to 0.5 into 10 power minus 3 meter cube. Okay, so this can be converted into mass as so that means we have to simply multiply with the density, which is 1000 kilogram per meter cube, and then the volume in meter cube, which is 0.5 into 10 power minus 3 meter cube. So ultimately this will come equal to 0.5 kg. Okay, and what is the specific heat for water? CW, that is given as 4200 with the appropriate units, which are joule per kg per Kelvin, and further information, that is TWI, the initial temperature of the water, that was 20 degrees Celsius, and TWF, that is equal to 23 degrees Celsius. Okay, so with this information we can solve this problem by making use of the principle of calorimetry, which says that the heat, because initially the aluminum was at a higher temperature, so that means it will lose the heat. So heat lost by aluminum, this is equal to heat gained by water. Okay, so now the heat lost by aluminum is equal to mass of the aluminum multiplied by specific heat of aluminum, okay, and the temperature difference, because the temperature has fallen for aluminum. So here the temperature of aluminum, which is initial, which is larger than the final temperature, minus aluminum temperature, the final aluminum temperature, and that is equal to mass of water, the specific heat of water, and then multiply by delta T. Okay, so delta T, because for the water there is a rise in temperature, so TW F minus TW I. Okay, now we have to simply plug in the values of all the quantities which are given to us, and except the one quantity which you have to find, which is T aluminum F. Okay, so if you do that, so M aluminum, this is 0.1 kg, and then multiply by specific heat of aluminum, which is given as 900, so put its value here. And then the initial temperature of aluminum is given as 95 degrees Celsius, which is 368 Kelvin. Okay, so that means 368 minus T aluminum final, and that is equal to mass of water, which is 0.5 kg, multiply by specific heat of water, which is 4200, and then the final temperature of water, which is 296 Kelvin minus 293 Kelvin. Okay, remember that now the temperature value that we will obtain, that will be in Kelvin, not in degree Celsius. Okay, so here after solving this, these two zero, they will cancel with each other, and after multiplication we will obtain 9 into 368 minus T aluminum final, the final temperature of aluminum, and that is equal to, after multiplication we will obtain, this is 210, and then the delta T, which is merely 296 minus 293, a factor of 3 basically. Okay, and let's come this side. So this, after doing the calculations, so we will obtain 3312 minus 9 aluminum final temperature, that is equal to 630. So after solving this result for the final temperature of aluminum, that is T aluminum final, that will be equal to, so okay, so this is basically equal to 3312 minus 630 divided by 9, and this is equal to 2682 by 9, and this is nothing but 298 Kelvin. Okay, so therefore in degree Celsius this can be written as T aluminum final, this is equal to 298 minus 273, and this is equal to 25 degrees Celsius. So this is our final answer. So the final temperature of aluminum is how much? It is 25 degrees Celsius. So that is our answer. If there is a 10% decrease in the atmospheric pressure, so that means dP, that is equal to 10% of atmospheric pressure. Okay, so that means dP, this is how much? 10%, that is 10 divided by 100, so that will give us 0.1, and of atmospheric pressure, so we have to write it in terms of Newton per meter square. So 1 atmospheric pressure is equal to 1.013 into 10 power 5 Newton per meter square. Okay, then the change in the boiling point, next the statement, then the change in boiling point of the water. So we have to find out what is the change in boiling point of the water. Okay, so that means we have to calculate the dt basically. Okay, so the information which is given to us, it's the latent heat of vaporization, that's also given to us. This is equal to 2.70 kilojoule per kg, and the change in specific volume at the boiling point. So boiling point is 100 degrees Celsius. 100 degrees Celsius, so that means this is nothing but 373 Kelvin, and the change in specific volume, so that means it's the V2 minus V1. This is given as 1.2 meter cube per kg. Okay, so now let's write the Clausius-Clapeyron equation, so which is dP by dt, okay, that is equal to L upon T and then multiply by V2 minus V1. Okay, so this is our equation number 1, and from here we can calculate the dt, because we are supposed to calculate the change in temperature, and dt can be rewritten as T multiply by change in specific volume during the transition, and then multiply by dP and then divided by the latent heat. Okay, let's call this a equation 2. Now we have to just make the substitution for all of these parameters which I have written earlier, and then substituting the value of all these parameters, the dt corresponding change in temperature turns out to be equal to dt, that is temperature, which is 373 multiplied by V2 minus V1. So V2 minus V1, that's a change in specific volume, okay, during the phase transition, which is 1.2, okay, and then multiply by delta P, dP, okay. So dP is how much? So I have written it here. This is equal to dP multiply by 0.1 into 1.013 into 10 power 5, and then divided by L, latent heat. Okay, so this is 2270, and then it is kilojoule per kg, so we have to write it in terms of joule, okay, into 10 power 3. So after doing the calculation, so we will notice that this is approximately close to 2 degrees Celsius. It's 1.99 something, so we can write it safely as 2 degrees Celsius. So therefore our answer is 2 degrees Celsius.